What is up, everybody? How's it going? It's Ken Q here, and today we're going to be doing some work with a microcontroller. I'm actually really excited about this. It took everything in my power not to just start playing with this microcontroller offline, but now we're here and we can get right to it. I'm going to put on some background music real quick. Let's see. There we go. And we're going to get right to it. So welcome to my laboratory here. I'm going to be moving my mic around a little bit while we're doing this because at certain points I'm going to be playing with the actual electronics and certain points we're going to be programming. So if you hear the springs of my microphone stand, it's because I'm moving my microphone around. And I apologize, but there's nothing I can do about that sound, unfortunately. Yeah. So this is my lab. Hope you like it. It's got a nice view of space. I've got my coffee, and we are ready to get started. So I'm just going to really quickly show what we have here. Ba-bam! Take a look at that. So here I have a breadboard with the aforementioned ATTINY44 microcontroller on it. It's got 14 pins, if I can count correctly. 7 on one side, 7 on the other side. I've already got it plugged into the breadboard here. I've also got a programmer for the microcontroller, and we'll be using that to interface to it and hopefully write some code to it that will make a light blink. So that's the goal. And I'll probably be switching back and forth between displays depending on whether we are actively programming and searching things up or whether we're actively wiring and unwiring things here. So to begin with, let's see, where do we start? So this programmer is actually one that I purchased from, what's the website? Adafruit.com. And it's one that you get the parts and you assemble it, solder it all together, and all of that. I was a little bit worried because I bought this a while ago and I never tested it after I assembled it, like 7 years back. And so I was a little bit worried that maybe it wouldn't work. But I plugged it in and I tried a few things out the other day, and it does, in fact, work, as far as I can tell. But to get started, I guess I will show you some of that it works, and what we're going to do. So I'm just going to switch over to this other display here. So obviously, since we're working with the microcontroller, we need the data sheet for it, because there's going to be a whole lot of stuff we need to look up and keep track of and reference as we go. Data sheets for microcontrollers are really detailed. They're many pages long, but they are extremely, extremely invaluable when you're working with these things. Now, personally, I've never worked at this level with a microcontroller before. In the past, I've worked with Arduinos and things. I have one here that I might use to power it after we're done programming. But I've never worked at just the chip level. So I'm excited. I want to do the programming of it in just the assembly instructions for the microcontroller to get that nice, simple, small program going. So to begin with, I have a command prompt here, because what I'm going to do is I'm going to plug in the programmer. And I have some software installed, so I guess first of all I have the drivers for this programmer installed, but I also have WinAVR installed. It's instance, this is an AVR microcontroller, and it comes with a program called AVR Dude, which is used to do various things to AVR microcontrollers, one of which is loading the code that you write onto it, and another one is setting the fuses and things like that, as well as, doing some checks and things like that of your microcontroller. So it's kind of an invaluable tool. What I can do is simply go, let's see, P, USB tiny, and dash, what is it, C? Let me check the reference here. Reference, yeah, C. And since mine is the ATTINY44, it's T44. And since it's not plugged in right now, I should get an error, but it should at least recognize. Whoop. Do I have that backwards? I do. You'd think C is chip, but it's not. USB tiny, USB tiny. And actually it should be here. Yeah, USB tiny. And then dash P is T44. There. So it at least knows that it's connected to this programmer, but it's not actually connected to the microcontroller. So it's saying, I don't see anything. So what we're going to do now is I'm going to flip back to the bigger view. Actually, maybe what I'll do is I'll just make the camera bigger on here for now. Whoops, that's not the button I wanted. Make the camera bigger. Transition over here. Good. So we're going to need the pinouts listed here. I also have a diagram somewhere. Here we go. This is the programmer schematic. And you can see up here in the top left, we have the pinouts for the connector. However, I don't actually know the orientation of this. The schematic doesn't really tell me here which way is which. And when I looked in the past online to try to figure out which pin is which, they reference the red line on this cable, but I've seen pictures with different orientations and things. So in order to connect that up, I'm actually going to figure out what the pinouts are in a second here. And then connect it. So to figure out what the pinouts are, I'm going to just make a simple circuit, and I'm going to try to figure out which pins are power and ground. And you can see on the schematic that power is this top left power, this pin 2, and ground is this bottom left pin 6. So they're on the same side of the connector. One's the top and one's the bottom, but we don't know which. So what I'm going to do is I am going to put an LED on my breadboard with a resistor. And I am going to pick 2 of these pins and attach them to one side of the LED and one side of the resistor, and then the other side. And basically, once it turns on, I've got power and ground in the right spots. So let's see here. Nope. Flip that around. There we go. So green is power, this green cable, and white is ground. So you can see where I have them plugged in. I have power and I have ground. Green is power, white is ground. So I can go ahead and if I, is there a way to show both of these at the same time? So white is ground. Ground is the pin 14, which is over here. And power will be pin 1, VCC over here. And now all I have to do is connect the rest of the pins up. But now that I have a reference, it makes it significantly easier to figure out where the rest of the pins are. So, sticking to that same side, the one between power and ground is MOSI, and MOSI is on pin 7. So let's go ahead and stick that in here. And stick that in there. Good. And then on the other side, pin 5, we have reset. And reset is pin 4. 4. 4. 1, 2, 3, 4. And then we have SCK at pin 3, which connects to pin 9. I really should get an actual connector for this, but it's fine. It's casual. And then finally, pin 1, miso. I could go for some miso right now. Gets connected to pin 8 over here. So in theory, that is all now connected up properly to the microcontroller. So I am just going to go ahead and close that. We're gonna shrink down this camera now that you've seen what I did. And we'll try this connection one more time, see what happens. Error, transmit. A device attached to the system is not functioning. Could be because I've been plugging and unplugging things while the power was on. We'll give it a second, we'll try again. Could also be that any one of my connections are loose, so just double check. Everything is still good. Some of these cables are a bit old, so they're a bit suspect. And we could also try restarting the controller itself. There we go. Sometimes you just gotta reboot. So AVR device initialized and ready to accept instructions. Reading blah, device signature blah. Fuse is okay. AVR dude done. Thank you. You're welcome. All right, so we can talk to this thing. That's been established. So there's a few things we can do now. And that is what? So we are going to read the fuses. So I just got to get the command for reading and writing to the thing. -U. What was dash lowercase e? Because the example used a lowercase e. No, I don't want to erase it right now because it doesn't matter. So -U, mem type, OP, file name, and format. So all memory types currently known are, so there's 3 fuses. There's the high fuse, the low fuse, and the extended fuse. So these are like generic configurations of the microcontroller. So they kind of decide how things are going to operate overall. And then, of course, the program itself will tell it what to do with all of that. So what we want to do is we want to read these things out. Now, yeah, so we can read it. Can we read it to a file? It's going to be an 8-bit thing, right? It's going to come out when we read it. So let's try it. All of that, and then -u, hfuse, :r, maybe if we go to desktop, just to make sure that we're actually writing this to and then ATTINY folder, -u, hfuse, do I need it though? Invalid update specification. All right, well, I'll write it to a file. hfuse.x. Sure. AVR device initialized, ready to accept instructions. Reading, device signature, reading hfuse memory, done. Writing output file to that, error. Invalid output file format, write to file failed. Okay, what about? It's because it doesn't exist, eh? It wrote something. Let's see. Notepad. Auto detected as invalid file format. The file name field, read and write, the format field is optional and contains the format of the file. Values are note if the file name contains a colon. All right, let's see. Let's make it a just force it to be hex. There we go, that worked. There. 0df. Okay, so we have hfuse. Let's do lfuse. And let's do efuse. All right, so now we've got them all written out. What we're going to do is we're going to figure out what the heck they mean. Let me just, I'm going to actually open these in Notepad++. Okay, H fuse, L fuse, E fuse. Okay, so what? Can I change this to binary? Let me just open up the data sheet and go to the fuses section. Is there a table of contents? Come on. I just want the section that describes all the fuses. Almost there. Here we go. So fuse extended byte, 1 unprogrammed. So I don't really care about that. I have a way to program it, so I'm just going to close the E fuse. We're going to start with H fuse. Let's see. So I want a hex to binary converter. I'm just going to find one online. Hex to binary. Rapid tables. DF. Convert. That's a beautiful thing. And then the L fuse is 62. Convert. There we go. All right, what do we got? External reset disable. 1 is unprogrammed. So it's unprogrammed, which means external reset is enabled, which I think we want. I think that's not something we're going to mess with. Debug wire, I don't really care. So we'll leave that as it is. Serial program and data downloading. Sure. 0 is programmed, which means SPI program enabled. Okay, sure. It's not gonna change my life. Next one is watchdog timer always on. We don't want it always on. We want it on if we configure it on. And then we have EEPROM memory preserved through chip erase. We don't want that either. I don't think we'll be using the EEPROM initially, just the flash memory. But if we ever need to, we can come back and change this. Right now, it's not preserved. And then the last 3 are brownout detection. And I'm not going to be playing with the brownout detection right now, so that's fine. We don't need to change that. For the low byte, let's see. We have clock divide by 8 right Right now it's unprogrammed. So I don't know what the clock is right now. I'd have to check that section. We'll come back to that. Next, clock output enabled. I don't want clock output. Yeah, I don't think we need that. Startup time. We're not going to mess with that. The defaults will be fine for that. And then the clock select clock source. 0, 2, and 3 are selected. The default setting results in internal RC oscillator at 8 megahertz. Okay. We're just going to check the system clock prescaler. Can be divided by setting that. Yeah, we're not going to mess with that. So the default fuse settings are actually completely fine. So that's good. That's really good. We're not going to change that at all. So we just close Notepad now. So now, the real meat and potatoes bit is that I want to connect a light to the output and program the microcontroller to control the light on and off, essentially. Like on, wait a bit, off, wait a bit, on, wait a bit, off, wait a bit. So I think I'm going to do it through one of the digital outputs. And I'm not sure which one yet, because I got to read through what each of these do. Analog to digital converter. Oops. TOAN, AREF, ground. Let's go port B. What's on port B? There's only those 4. PC int xtal, PC int reset DW, PC int UC CK out. As inputs, port B pins that are externally pulled low. If the pull-up resistors are activated. As inputs, okay, to use pin PB3, oh, that's fine, I don't need to do that. Port A, bidirectional, 8-bit bidirectional I/O port with internal pull-up resistors selected for each bit. Port A output buffers have symmetric drive characteristics with both high sync source capabilities as inputs. Pull low source current. Externally pull low source current if the pull-up resistors are activated. So it sounds like I could use either A or B to do this. And what I'll want to do in that case is take my LED, connect it to the pin of the microcontroller, through the resistor to ground, and when the pull-up resistor is activated, it'll turn the light on, and when the pull-up resistor is deactivated, it'll turn the light off. Maybe. Now, normally the more correct thing to do would be to take one of these output pins and actually run it to a transistor and then have the LED powered off the transistor. But I don't have one at the moment. I'll get one eventually. So I'm just going to run it off the microcontroller. But there are cases where running directly off the microcontroller could be damaging to the microcontroller. But in this case, we should be okay. Underline should. Yeah. Pull up. If this signal is set, the pull up enable is controlled by POV. Reading a pin value, switching between input. Here we go. Writing a logic 1 to pin blah toggles the value of port blah independent of the value of blah. Okay, hold up. Ports as general I/O. Good. Here we go. Each port pin consists of 3 register bits, DD, port, and pin. DD bits are accessed with DDR I/O address. Port bits are port X I/O address, and pin with pin. DD bit selects the direction of this pin. If it's a 1, it's configured as an output pin. If it's 0, then it's an input. So we're going to want to pick a port or pick a pin. Pick a pin and make it the output. So then port XN is written logic 1 when the pin is configured as an input. To switch the pull-up resistor off, port X is written logic 0 or the pin has to be configured as an output. To switch the pull-up resistor off, output pin. Port pins are tri-stated, blah. There we go. So that's what we want to do. We want to set it as an output and then write to port blah, logic 1 to drive it high, and then logic 0 to drive it low. Okay, so we're going to decide right now. Put this back in here. Boop. Which pin we're going to use. And I think the answer is going to be this pin over here. Pin 12. Is going to go back to ground. have a loop. Right now, that port is not configured to do anything, but we are about to set that up. So what? Let us start making a program. All right. Microchip Studio. New project. Assembler. AVR assembler. Name will be blinking LED. And we will put that on the desktop. Create directory, beautiful. Device selection, ATTINY44. Okay. So I what? I need to know what pin I plugged that into. So let's see. PA1. Okay. So we're just going to LED on PA1. Okay. And now I have no idea what I need to do. So there's a start. I've never programmed in assembly before, so I literally have no idea what I'm doing now. But I think there is some reference documentation down here. Here we go. So all I want to do is set the register DDA bit 1 to output first. So set register SER operand RD, so that's the register I want, and then I have to provide a value. I'm not sure what INCR16 is, so I'm not going to delete it just yet. DDA. And I need to know what that register looks like. Oh, set bits in register. SBR might be it. I wonder if it works like this, where I can set it before the start. Because I don't want to have to set it every single time. Just the once. And then here, that's probably going to be an SBR as well. to the register definitions. DA. Define pull-ups. Port A4, LDI, and then output on port A. Pins 0, 1, and 4. Two and 3. This is interesting. So what they're doing is they're loading into a temporary register some values. And then they're outputting that to port A and DDRA. Why does port A need to be set first? And what is a knob? You got to give it a cycle to assign before reading back the values. Okay, so I'm going to borrow that code. LDI R. Okay, I want to look up the INC instruction. Okay, let's remember this page 57. INC increment. So I don't want INC. Maybe I need to set the direction every time. So we're just going to leave that out. Okay, so LDI. I just want to look up LDI as well. Where is it? Load immediate. Data transfer instructions. Okay. I wonder why they do that instead of SBR. SBR? Set bits in register. Oh well. LDI R16, comma, and then it was 1. I want that to go to port A. Sorry. I've already forgotten the example. Back up to 57. Please. Port A4. So in my case, it's port A1. And then LDI into R17. 1 to DDA1. to port A R16, out to DDRA R17. Out port A R16, out DDRA, is it? Yeah, DDRA R17, NOP, and we'll do the read in of pin A in R16, pin A, R16, pin A. Okay. So in theory, that should turn it on. And then what we want to do is find a sleepy time function. Sleep. Sleep. But is that the sleep that I think it is? Or is there like a wait instead? Branch if, compare, indirect jump, interrupt return. Blah. All right, we're going to look up the sleep. I wish it would point me to a section. Like, come on. It doesn't really tell me much. Sleep enabled. Okay. So I think what I need to do is start a timer on an interrupt, go to sleep, wait for the interrupt, have it wake up, do the next action, and repeat. Yeah. Let's try that. So I would need to set MCU-CR bit 5 SE. So let's just put some space here. MCUCR 1 to SE, maybe. And then there should be a sleep command, and then SBR, set it off. In theory. Doop, doop, doop. Yeah, it still does an LDI and an out. MCU SR. I might do that. R17. Copy the same thing here, except we'll set it to 0. I'm going to put spaces in. I don't know if they're necessary, but okay. Interrupt. So I want some sort of timer interrupt. Address, labels, code, comments. Address, labels, code, comments. Low level interrupt, pin change, timing interrupt. MCUCR, that's all fine. IO ports. Port says general IO. Yeah. Alternate port functions. Sleep control. Alternate functions. that's what pin A does. It's the inputs. So in the example, since they configured some of them as inputs, then yeah. Why is that yellow? I wonder why that's yellow. Anywho, I'm going to keep going. Timer. TOV, OCF. What I really want is I want this thing to sleep for a bit. Just wait. I don't want PWM. I don't want waveform generation. Timer counter interrupt mask. Output compare. Oh. Gives direct access both read and write to the timer counter unit 8-bit counter. Writing removes the compare match on the following timer clock. Modifying the counter while the counter is running introduces blah. Yes, that's fine. Okay, so the timer counter register. Learning a few things here. It's gonna take me a minute. The bit is set when an overflow occurs in counter blah. (16-bit) input capture, output compare. Maybe the internet has a suggestion. That might be something to double check. AVR wait function. Time delay in AVR microcontroller. Instruction cycle times, yeah. time delay. That's in assembly. Okay, how about for now, we just get it working. Do I need this start? Right, like shouldn't that be enough to turn it on and leave it on? So how do I build this thing? Build. I have a blinking LED.hex file. Well, let's give this a whirl then. If I have blinking LED.hex, let's copy it into, it's not blinking, but you know, let's get our reference manual out here. We want to write this to flash. Flash, write, blinking LED.hex. Hey, look at that. The light went on. What the heck? I'm going to call that LED on .hex, and I'm going to make one that's LED off. Oops, I just named it LED off. It's supposed to be LED on. LED on.hex, and let's bring back Microchip Studio. Direction is fine, but let's drive it low. And let's build that. Success. And let's copy it here. We'll call it LED off.hex. And we can send LED off. And the light goes off. Whatever. Beautiful. Okay. So now we know some things that work. And think that's plenty for now because I clearly have a lot of reading to do. But what I want to do next time is I want to set up this wait thing. And I think what I want to do is set it up so that, I don't know, maybe the clocks, set the clock to be such that I can cycle this thing on and off based on comparing the clock. Right? That's what I want to do here. Here. This thing, whatever it is, TCNT. Maybe not the 16-bit one, but the 8-bit one. Yeah, output compare register A or B, continuously compared to TCNT0. A match can be used to generate an output compare interrupt. So basically, I'll set OCR0A to, I don't know, something based on what the clock rate is, right? And then it will do the compare. So I'll turn the clock on, get it to do the turn the clock on, no, set the compare value, turn the clock on, go to sleep. The interrupt when the compare hits the value will wake it up. Turn the clock off. Set the output to nothing. Set the output compare register. Turn the clock on. Actually, I feel like I could do this now. Okay. So let's turn it on. LED goes on. Next. Next will be LDI R16 some value. Let's just say, and then out OC what? OCR0A. OCR0A R16. And then it would be a matter of setting the clock. I don't know how to set the clock. Okay. That would happen. And then there would be a sleep. It would get woken up. Something else would happen. It would set this to 0. And then all of this would happen again. So that's good. all I need to figure out now is how to set this up. When a compare match occurs between the timer counter, cleared by hardware when executing the corresponding interrupt. OCIE0B SREG. Okay, I gotta go up to there. OCI TCCR timer counter control register B. Force output compare. Clear OC0A on compare match when up counting. What? TCCR0A. Toggle OC0A on compare match. Interesting. Very interesting. So I can just keep cycling, and every time it matches, it'll just flip the bit. And if it flips the bit, then it could be set to the same value here. How do I do that? Okay, so I need a 0 and a 1. So this should be set at the start, I think. LDI TCR16 0 to, which one was it? To COM0A1. COM0A1. And set 1 to COM0A0. Out to, what register was that? TCCR0A. So that means it'll toggle every time. Okay. referring to the OCOX state, the reference is for the internal OCOX register, not the OC0X pin. That's fine. The simplest mode of operation is normal mode, WGM02. Wait a second. WGM01. COM0A, COM0B. Yeah, normal mode. So much scrolling. Oh my gosh. The counting direction is always up and no counter clear is performed. The counter simply overruns when it passes its maximum 8-bit and then restarts from the bottom. In normal operation, the over flag will be set in the same time clock style. TOV flag in this case behaves like the 9th bit, except that it's only set, not cleared. However, combined with the timer overflow interrupt that automatically clears the TOV0 flag, the timer is the output compare unit can be used to generate interrupts using output compare to generate waveforms. In normal mode is not recommended since this will occupy too much of the CPU time. Clear timer on compare match. CTC mode. The counter is cleared to 0 when the counter value matches that. Yeah, let's do that. WGM 2 to 0. CTC. So WGM01 needs to be set to 1. And WGM00 needs to be set to 0. Just like that. Allegedly. So then yeah, that. Actually, I can set this before there because the compare value should not change. Okay. And then we just need to set the timer. TCCRB. Force out compare. select. Let's set that. So TCCR LDI R17. Which ones do we want? We want CS2 to be 1, CS1 to be 0, 0 to be 0, 0 to be 1. My music stop. Let's get that going again. Zero, oops, 0, CS01, and 1, CS00, out, TCCR01. That's not right. It's going to be 0A, isn't it? Yeah, 0A and 0B. R 0B 17. Okay. And I still gotta set that interrupt, but I'm not sure how yet. OCR A, yep. Interrupt mask. When the current to 1 and the I bit in status register is set, the timer counter is executed if a compare match on timer OCF bit is set. Okay, so I need to set this. Time SK. LDI R16. What do we need? OCIE 0A. Out. SK 0. Team SK 0. R16. I don't technically need to do all these LDIs, I can just out and then a hex value, but for the sake of learning and understanding, I'm going to do it. Okay, now I got to figure out how to set up the interrupt. Gosh. Okay, change mask, general interrupt register. Okay. Interrupt mask. Okay, there we go. MCU control. doesn't. That's external interrupts. Here's interrupts in general. Set global interrupt enable. Is that it? SEI? Okay. That doesn't really... Clock sources, 8 megahertz. Low frequency crystal oscillator. Clock prescale. Sleep. Yeah, so I just need to set up the interrupt. does this mean? So address, label, code. All I need to do is set that to essentially NOP, because it'll just wake it up from sleep, right? Label, code. Do. Okay, IO ports. Output compare. I think that's it. I have CTC. So in theory, what should happen is we set everything up, we go to sleep, do it again, and we go to sleep again, and we start over. Syntax error, unexpected integer. Where? Line 12. Where's the line numbers? 12. Okay, well, I clearly have no idea what I'm doing there. Input capture. I need to know how to set the interrupts. Maybe I'll just Google it. ADR assembly set interrupts. .org. Somebody used .org in front of this. Not .org, just .org. Okay, something worked. Let's give that a shot. Blinking LED. I don't see blinking, but I do want to check something. I think it is blinking. It's blinking, but it's so fast that it's just dimming it. Okay, so there's a clock thing, right? A C cell. MCUCR. Okay, I'm just gonna transfer the LED on because I don't know how fast it's blinking. Oh, do I have that set? MCUCR SE bit. Where's MCUCR? Did I not configure MCUCR? My bad. LDI R17. What do we need to configure for MCUCR? Sleep enable, SE, yeah. Sleep mode, okay. SM1 and SM0. Idle, 00. Don't care about those. So MCUCR. So 1 to sleep enabled. And 0 to sleep mode 1, I think it was. SM1. And 0 to SM0. Out MCUCR R17. Bunch of configuration up front, eh? Okay. So was it sleeping or was it not sleeping? Okay. We'll load it up real quick. It went off first, then it went on. And now it's probably just asleep right now because I'm not getting an interrupt because something wasn't set yet, which is fine. Ah. So MCU status register, power on reset, blah, blah, blah. Control. Okay. interrupts. Program address and source 6, right? 6. Ah, timer counter 1. I want timer counter 0. So I want 9. Wow, that's a... Let's try that out. Make sure that wasn't the thing. Yep. Doopy doopy doo. Do I need to do that? SEI? Nope. But I think we're getting closer. MCCR interrupt sense control. IO ports. Counters. It's a 16-bit counter. Let's look over the 8-bit counter real quick. Overview. Output compare. Prescaler. Okay. Timers. I feel like there's got to be something I'm missing, something major. All right, you know what? I'm probably just going to end it here for now. We got the light to go on, we got the light to go off. And now there's going to just be a matter of me reading through this a few times to understand some of the more nuanced things about setting up this interrupt that I want to set up. So I hope you guys have enjoyed. Probably the last 45 minutes have been a little bit dull, but yeah, I plan to get the blinking set up for next time. But also next time I want to kind of outline possibilities for where I go from here. I've got a few projects in mind, and I want these projects to kind of start at the design phase and move into obviously the prototype phase, then the build phase of like production, getting a PCB design laid out, getting it made, etc., to full assembly and then testing. So I'm not really sure what the project will be yet, but I'm hoping by next week I'll have a pretty good idea of where I want to go from here. So I hope you've enjoyed, and until next time, keep being yourselves. Bye.